where we stopped yesterday. Yeah, so I think the plan for today is that we are going to restart from where we stopped last times. And then during the second half of today's lecture, we'll continue the hands-on tutorial with the Orange software, where we'll talk a little bit about what we discussed yesterday with the calcium aluminosilicate data sets, and then we'll move to some example on how we can use this software to train some machine learning model. So what we discussed yesterday, like the point at which we stopped, was to define what is machine learning. And so we define it as follows. We say that machine learning is the science of getting a computer to learn how to perform a given task by example, without being explicitly programmed on how to perform this task. So the idea being that you will have some data, you will expose the machine learning model to those data, and the machine learning model will learn how to make some prediction just by example, just by looking at historical data. And the outcome of the machine learning model, it will give you the rules. It will give you some rules on how to make some prediction based on data. So we'll see some example about this today and some different algorithm on how you can achieve that. So like I think there is three main steps that you need to follow when you work with a machine learning model. So the first thing is that you will need some data. So since everything about machine learning is you never learn anything based on some pre-existing rules, you only learn by observing data. So if you don't have any data, then you cannot train any machine learning model. So that's the first thing. It's to ensure that you have some data. And so those data is what we will use to train the machine learning model. So this is what we will call the training set. The machine learning model will consider those data and trying to find those some patterns with those data to then use those patterns to find some rules on how to make some prediction based on those data. So that's the step two. This is the step that is called the learning. This is where the machine learning model is exposed to the data and learns something based on those data. So the idea, for example, is that if you look at the weather over the past years, then you would be able to, based on those historical data of the weather, the temperature, is it sunny or cloudy, based on the past years, now you find some pattern that makes it possible for you to predict in the future what will be the weather for tomorrow, for example. So this is the process of learning. You look at existing data. You don't know anything about the science that controls the weather, but just by looking at previous weather data from the past year, now you become able to predict what will be the weather for tomorrow or the day after tomorrow. So that's the process of learning. And then once you have learned something, now you become able to make some prediction for the future, for data that you have never seen before. So that's the next step is, so first the training, then the learning. And once you have learned, then you become able to make some prediction. And ultimately, when we train some machine learning model, it's always to make some prediction. We want to use this to make some prediction for the future, or to make some prediction about, for example, glasses that the model has never seen before. So a few examples of this. So for example, let's assume that you have a data set of, let's say, glasses, and you have different glasses. You have their composition, like maybe you have how they were made, like the cooling rate or the types of annealing that was performed on those glasses. And maybe you have the density of those glasses. And your goal here is you want a model that can predict the density of glasses. You want a model that can learn how to predict the density of glasses as a function of their composition and as a function of their thermal history, for example. So for this, you would start with a data set of existing glasses where you have at the same time the composition the annealing temperature or the annealing duration and the density. So this would be the in this case the composition and the manufacturing condition. That would be the input. This is what you will use as your variable, and the density, this is the output. This is what you want to predict. But in the case of machine learning, you need to start first with a data set where you have at the same time the input and the output. And so this is what you will use to first like have your training data set. So then once you have this, then you will go to the process of learning. So you will learn, you will expose those data to your model, and you will try to have your model learn the relationship between composition and density. So this is the process where the model try to find some patterns in the data, try to find some relationship between the composition and the density, and try to learn how in the future it will be able to predict the density of glasses just based on their composition. And once you have this, once this is done, once the model has learned, then you can move to the prediction. It means that now you can take new glasses with an arbitrary composition, so including glasses that we are not used to train the model, and the model will be able to predict the density of those glasses. So this is the first step. First, you take some data, then you learn based on those data. And once you have learned based on those data, then you become able to make some prediction. So this is the three basic steps of machine learning. Okay, so now let's start to talk a little bit more specifically about the different types of machine learning model and some algorithm on how to achieve those tasks. So there is, I would say, two main families of machine learning model, which are called either unsupervised or supervised. And we'll see some example about what's the difference between those two. So let me first give you some definition, but then I'll show you some example, which hopefully will make it clear if the definition itself is not clear. So basically, so you have those two categories of machine learning model, unsupervised and supervised. Unsupervised machine learning are techniques that can look at data and try to find some groups within those data. So an example of this would be, let's assume that you have a series of glasses and you know their composition, but you don't know anything else about those glasses. You don't have any label. So you don't know, for example, if those glasses belong to different family. You don't know any property of those glasses. So you don't have any label for those glasses. The label would be either a name of the group that this glass belongs to, or some properties that you would be interested in predicting for those glasses. So that would be a label. So if you have data that do not have any label, that is to say, for example, just a list of thousands of glass composition with nothing else. One aspect of what you can do with machine learning is to consider those data and try to group them into groups of similar data. And in that case, that's something that would be an unsupervised learning case. You don't have any label for those glasses. You just take those data, you just take those glass composition, and you just try to group them into groups of glasses that look similar to each other. So that's one first type of machine learning model. This is called the unsupervised learning. Basically, the only idea is that you take some, you only have some inputs, like for example, some glass composition, and you just try to group them. You try to find some similarity between glasses and to group them together. So that can be, in certain cases, useful if you just have a large number of glasses and you want to find some groups of glasses that are similar to each other. Another aspect of this that is quite commonly used is to find outliers. if you find that there is a large number of glasses that look similar to each other, and then there is one glass that look very different from the rest, then it's possible that this is an outlier, and that there might be like a mistake on its composition or something like that. So these types of unsupervised learning is typically done to do some clustering. That is to say, to find some clusters of data points that are similar to each other, for example, some clusters of glasses that are similar to each other, or to find some outliers, to find glasses that seem to be very different from the other. So that's the first thing. That's unsupervised learning, and I'll come back to that with some example in a few slides. The second types of machine learning is when you have data with some label. That is to say, when you have something that you want to predict about those glasses, and you already have some example about glasses for which you know already the property that you want to predict. So for example, now let's assume that you have a series of glasses, and you have a data set where you have a large number of glasses with their composition, but this time you have a label. So for example, you know that those glasses are like window glasses, or that those glasses are, let's say, I don't know, display glasses or cover glasses or bioactive glasses, things like that. So you have a label already, you know that those glasses belong to different families. Then in that case, that becomes a supervised learning problem, because now those data have a label. They have something that you can predict. So then once you are in this category, when you are in the category of supervised learning, then it means that you have an output that you will want to predict, some either a glass property, or a group, a name for the group of glasses that this glass belong to. So there is two types of supervised learning. The first one is classification. Classification is when you want to predict a category. So for example, if you have a series of glass composition and you want to predict what type of glass it is, you want to predict based on the composition if it's going to be a window glass or a bioactive glass or a nuclear waste glasses or something like that. So in that case, you are trying to predict a category. You're trying to predict among a list of groups what groups this glass belong to. And so for this, you already have some example of glasses for which you already know which group they belong to. And you will use those data to train a machine learning model that can learn how to map the composition of a glass to the group it belongs to. And then this machine learning model will be able for the future to take new glasses it has never seen before and tell you if it's a window glass or a cover glass or a display glass, etc. So that would be a classification problem. You have a glass composition that you use as an input, and you try to predict a category based on that. You're trying to predict if what types of glass it is. There can be some other example of classification. For example, if you have like a melt composition and you want to predict if this melt is going to form a glass or if it's going to crystallize as you quench it, then that could be another classification problem. You can have you would have, like, for example, a data set of glasses for which you would know their composition, and then you would have a categorical information about each glasses. You would say this glass, well, this melt will form a glass, or this melt will crystallize. And so for each melt composition, you would say, does it crystallize or does it vitrify? And then based on that, so again, each data has a label. This label is a category. Either it vitrifies, either it crystallizes. And then based on that, you can train a machine learning model that would, based on the composition of a glass, would predict if it crystallizes or if it's going to vitrify. So that would be a classification model. This is when you want to predict a category. The last type of supervised learning would be a regression problem. A regression problem is when you want to predict something about this glass, which is a number. So unlike groups of glass, like cover glasses, display glasses, or window glasses, and unlike does this glass vitrify or does it crystallize? So those were categorical variables. If what you're trying to predict is a number, for example, you're trying to predict the density of a glass, or you're trying to predict the modulus of a glass, or you're trying to predict the glass transition temperature or the liquidus temperature of a given system, now you're trying to predict a number. And if you're predicting a number, that becomes a regression problem. So that's the last types of supervised learning. In that case, what you would need is a data set of glasses for which you already know their composition, and you know the property that you're trying to predict, like density, modulus, liquidus temperature, etc. And based on that, the model will look at those data and try to learn how to predict this property, how to predict the density of a glass based on its composition. And once the model has learned, now it's going to be able to predict the density of glasses, even for glasses that it has never seen before, even for glasses that were not included in the dataset that you use to train the model. So this is basically the two families of model, the two families of machine learning model. Unsupervised is when you do not have any property that you want to predict. You just have some input, some glass composition, and you want to group them together, for example. Supervised is when you have something that you want to predict. And this prediction can be either a group, in that case, that's classification, or a number, in that case, that's regression. So we're going to see some example about those three types of machine learning model, and then we will see how to implement some example of such model in the Orange software. So let's start with unsupervised machine learning. So again, unsupervised machine learning, you do not have any label about the data. You just want to look at data and find some similarity between groups of data, to group them together, like to find some clusters of data points. So let's take this example here. So for example, let's assume that you have those this list of characters here, and you don't know anything about those characters. So you don't know that some of them are ducks, some of them are mouth, some of them are rabbits, etc. So you just have those characters and you don't know anything about them. You don't have any label. And so if your goal is to group them in terms of groups of characters that look similar to each other, what an unsupervised machine learning model would do is to look at those data, try to define some, to find some features about those data that they are influential at distinguishing those different characters from each other, or at some features that looks like they can be some similarities between those different characters. So what I mean by that is that if a machine learning model was to look at those characters, it would find some specific features that look similar between different characters. Like, for example, you have the two ducks on the top. The machine learning model would find that those two ducks, they have like two yellow beaks. So this looks like a feature that some characters have, like the two characters at the top and the character at the bottom, they all have this yellow beak. And then you have two characters that do not have this. So that would be an example of a feature that seem to, that some characters share in common and that some other character do not have. So that would be a good example of a feature that can be used to cluster data points together in groups that look similar to each other. But there can be some other features. You can look at the number of legs, but if you look at the number of legs, that would not be a good feature because all of those characters all have two legs. So in this case, the number of legs would not be useful to find some groups of data points that are similar to each other, because that's a feature that all the data points have. So it's not a very influential feature. Then you can look at the number of ears, for example. The number of ears would be an influential feature because, again, you have three characters that do not seem to have ears. and then you have two characters that have 2 ears. So that would be a good example of a feature that can be used to group those data points together. So that's basically the idea of unsupervised learning. You look at data, you try to find some features within those data that either can separate data points from each other, or that look like they are they capture some similarity between the data points. And so based on that, you are able to group those characters together. You find a first group of characters that look similar to each other because they do not have ears and because they have this yellow beak. And then you have a second group of characters that do not have beak and have 2 ears. So this is how you can do these types of clustering. These types of clustering doesn't tell you what type of character it is. It doesn't tell you that those are ducks, doesn't tell you that those are not ducks. It just tells you that those groups of character look similar to each other, but it doesn't tell you what they are. So that's what you can do with machine learning. You can group data points together based on their similarity, but it doesn't tell you anything, doesn't tell you any label about those data points. And on the other hand, if you had one character that was just found as an isolated cluster, like a third group of character that would be alone, then it's possible that this character could be some kind of outlier. It could be a character that is so different from the other that it looks like it's an outlier, that it could be either, I mean, if it was a glass, that could be some kind of mistake that makes this glass look very different from all the other. And in that case, that could be an outlier that would deserve to be inspected more. So these types of unsupervised learning is good to find either groups of similar data or to find outliers, to identify data points that are completely different from the rest. So in terms of, so that's pretty much what I said, but let's see some example about how it works. So let me switch to the iPad to show you like the basic idea about how this works. So give me a few seconds to make it work. Okay, so I'm going to show you like the main idea of clustering, of this unsupervised learning, and then we'll see some similar example for the supervised case. So here, so let's assume, for example, that you have a series of glasses, and you know something about those glasses. So you have certain features that you know about those glasses. So let's take an example where you have a series of glasses, and let's assume that you know 2 things about those glasses. So you know, on the one hand, let's say assume you know the density. So you know the density of those glasses. You have measured the density of a group of glasses. And assume that you also know the refractive index about those glasses. So you know their optical index. And that's the only thing that you know. You don't know anything else about those glasses, or at least you are not interested in predicting anything else. You just want to take those glasses and see if you can find some groups of glasses that look similar to each other. So then let's assume that you're going to plot this. So you have all your glasses, and for each of them, you know both the refractive index and the density. So now you can plot the glasses that you have. So you have some glasses like this, some glasses like this, and maybe you have one glass like this. So what unsupervised machine learning would do in this case is that it would consider those data points, and it would see how can I group them into groups of glasses that seems to behave similarly. And in this case, if you look at it as a human, of course, it looks like it's a very simple problem. It's a very simple problem because here you have only 2 variables. So it looks pretty obvious that you have one groups of glass here, another group of glass here, and maybe this group here that looks separated from the other. So in this case, it means that the algorithm would have found 3 clusters. So that would be cluster 1, that would be cluster 2, and maybe here a third cluster. So that's what the unsupervised learning algorithm would do. And again, it looks simple to do that if you have only 2 dimensions. But when you have hundreds of dimensions, when you have a lot of glasses for which you know their chemical composition, so you know the fraction of their mole percent of oxides, for example, or you know other properties about those glasses, like like their modulus, their glass transition temperature, their index density, etc. So if you know a lot of things about those glasses, then as human, we cannot really look at data points with more than 3 dimensions. So it becomes a very difficult task as human to find groups of glasses that are similar to each other if there are more than 3 dimensions, let's say. So that's something that machine learning algorithm can be very good at. Even with a high number of dimensions, they are able to find groups of data points. So here, if we come back to those examples, here, the types of outcome that you would get from this is that first, you have found 2 main clusters of glasses that look similar to each other. So that means that you have those 2 types of glasses that share some similarities. So that's one thing. And then here you have found one cluster that have a size of 1. So that would be potentially an outlier. So that's something that would need to be checked. If there is this glass that seems like the density and the refractive index of this glass doesn't seem to really match with that of the other glass, then it means that maybe there has been a mistake in either the way the density was measured. Maybe the density should actually be lower so that this glass would belong to cluster 1. Or maybe the density is correct, but maybe the refractive index was not properly measured, and actually this glass should belong to cluster 2. So this could be a real glass that has very interesting properties, but that would probably be a glass that you would need to double check, a potential outlier that needs to be double checked to make sure that its a refractive index and density are correct. So this is a very common use of unsupervised learning. It's to find outliers, to find some data points that do not seem right. And so that means that those points needs to be double checked. So that's useful to do this kind of analysis, to find some potential issues with data, to ensure that there hasn't been any mistake in experiments or anything like that. So that's useful if you have some data sets, to run this kind of unsupervised learning, to see if there could be any typo when you enter the data or any experimental mistake. That's useful to basically clean the data sets, to ensure that there is no data points that would not be correct in the data set. So that's the main idea about clustering. Like, is there any question about clustering? So we haven't really talked yet about how to do that in practice, like what would be the algorithm, but at least in terms of the idea of how clustering works and what you can do with that, like, is there any questions so far about this? Okay, so if there is no question, let's move to another example, which is now a supervised machine learning problem. So this was unsupervised because you do not know any label. You just find that there is a cluster 1 of glasses, a cluster 2 of glasses, but you don't know what those cluster 1 and cluster 2 correspond to. It's possible that some of them are 2 different families of glasses, like some silicate glasses, some borate glasses, something like that. But we cannot predict that with unsupervised learning, because in unsupervised learning, there is no label. You just look at groups of data points and find some similarity. Now let's consider a supervised learning problem. So that would be a problem that is pretty similar to the one we just discussed, but this time it's supervised. It means that we know some label about those glasses. So let's take an example again. So let's assume that again, you have a data set of glasses. And for those glasses, you know two things. So let's assume that you know their melting temperature. So temperature at which it will turn into a liquid. And you know the glass transition temperature. So the temperature at which the melt turns into a glass, freezes into a glass. And so you have some example about glasses for which you know at the same time the melting temperature and the glass transition temperature. But now you have a label, you know something else, you know a label, you know a property of those glasses. And that's the property that you will want to predict. And let's assume that in this case, you have two potential labels for those glasses. Either you know that the melt can vitrify. So you know that this melt, if you quench it, it's going to turn into a glass that looks like it's not crystallized, not phase separated, anything like that. And then you have for some other melts, you know that they will crystallize. So you have those two things. Either it's going to crystallize, either it's going to vitrify. And so let's assume that this is what you have. You have those glasses and you know their glass transition temperature, you know their melting temperature, and you know if they are going to crystallize or vitrify. So now what you can do is to look at those data points. So let's assume that you have a group of data points like this, where for those groups of data points, for those glasses, so you know their glass transition temperature, you know their melting temperature, and I'm going to put them in green because you know that those glasses do not crystallize, they vitrify, they turn into a glass as you quench the melt. And then you have another types of glasses for which, again, you know, for each of those glasses, you know the glass transition temperature and the melting temperature. But this time, you know that those glasses do crystallize. They do not form a glass, actually. So the melt, when you melt it and then you quench it, it tends to crystallize. It doesn't form a glass. So in that case, now that becomes a supervised learning problem. And more specifically, that becomes a classification problem. Because you are not trying to predict a number, you're trying to predict a category. You're trying to predict if this glass crystallize or vitrify. So now that becomes a classification problem. And in that case, what the classification algorithm will try to do is to consider those data and to try to separate, to find a rule that separates the melts that crystallize from the melts that vitrify. So for example, in this case, the kind of rule that that this types of classification algorithm would do is to say that if I take all the glasses that are above this line, they seem like they tend to vitrify, and the ones that are below this line, they seem that they tend to crystallize. So what the classification algorithm will do is to find these types of boundary. So this is what we call a classification boundary. It's a boundary that is going to separate the different classes. So this would be the first class of melts. That's the melts that vitrify. And then you have the second class of glasses. Those are the ones that do vitrify during the cooling. And so what these types of machine learning model does is to find the boundary here between glasses. And once you have found this boundary, it means that in the future, if you have a new point, so you have a new glasses for which you have measured its glass transition temperature and its melting temperature, here you would be able to say that since this glass is above the decision boundary, I predict that this thing will vitrify. On the other hand, if you had a new glass here, and again, you know its glass transition temperature and its melting temperature, now since it's below the classification boundary, then you would be able to predict that this melt will crystallize. So this is the basic step of a classification algorithm. You look at the data that you have. Based on the data, you find a decision boundary. You find a boundary that separates those groups of data. That's the process of learning. And once you have this, then you become able to make some prediction. You can take new glasses that the model has never seen before and use that to predict if they are going to crystallize or not. So this decision boundary here doesn't have to be linear. Okay, so in this case, I used a very simple example. So it looks like it's linear, but you could have some cases that would be more complicated. So let me just show you another example. Like it's possible that, for example, you could have some glasses for which you know two properties, X1 and X2. And then again, like you have some glasses that let's say would crystallize. So I would put them in red. And then you have some other glasses like this, and those glasses do vitrify, they do not crystallize. In that case, if you want to train a model that can learn how to predict which glasses crystallize and which one do not, then a linear decision boundary would not work in this case, right? So you would need, in that case, a model that is able to say that the boundary is something like that. Everything that is outside this circle would vitrify. Everything that is inside this circle would turn into a glass, right? Would crystallize. So everything inside would crystallize. Everything outside would vitrify. So the decision boundary doesn't have to be linear. It can have any shape. So, but the idea is still the same, is that you have some groups of data and you try to find a boundary that separates those data from each other, to separate the different classes from each other. And once you have this boundary, now you become able to make some prediction in the future. Again, here, I'm drawing something in 2 dimensions here. So it's very simple. Like you think that's something that you don't need machine learning to do that in this case. But if you know a lot of features about glasses, you know their glass transition temperature, their melting temperature, you know their composition, their density, refractive index. It means that now you will have a lot of dimensions, not only 2 dimensions, but many dimensions like this. And when you have many dimensions, grouping data together, finding boundaries between data points with a lot of dimensions becomes something that becomes almost impossible for humans to do. So finding boundaries when you have 2 or maybe 3 input features that you know about glasses, that's something that is fairly easy to do as a human. But once you have more variables, more than 3 variables, then it becomes something that is very difficult for humans, because we can only see data in 3 dimensions, not more than that. So those types of classification techniques become very useful, especially in high dimension, when you have more than 3 inputs, because that's something that becomes almost impossible to do for humans. Is there any questions about this classification thing? So again, like, yes.
Sorry, I was just going to ask. So I get that with the supervised learning, it allows you to have these labeled categories and you can distinguish between these inputs. But then what's the point of the unsupervised if it only gives you clusters with no labels, especially when you start, as you've just said, you start getting more than 3 dimensions?
Mm-hmm. But the unsupervised, it depends on it depends on 2 things. It depends on what's your objective, and it depends on what is the information that you have. For example, if you have a list of glasses, but you don't know if those glasses do crystallize or do vitrify, then you would not be able to use supervised learning, because you don't have a data set for which you already know if those glasses are going to form glasses or if they're going to crystallize. So then in that case, you have nothing that you can predict. So you would not be able to use supervised learning. So in that case, you can still use unsupervised learning because pretty much that's the only thing you can do. If you don't have any label that you can predict, the only thing that you can do is to look at the glasses that you have and see if there seem to be groups of data points that seems to behave similarly to each other. But in this case, again, it's if you already know something about those glasses, if you already know some label, if you already know a type of glasses, if you already know if they crystallize, if they phase separate or things like that, then it's probably going to be better for you to use classification and to predict this label. But if you do not have any label, then this is when you would use unsupervised learning, because in this case, you would not be able to use supervised because you do not have any label to predict. Does it make sense what I'm saying?
A little bit, but like with this example, refractive index and densities, obviously they're numbers, so can't they be classed as regression more so than classification?
So sorry, do you mind repeating that?
Sorry, yeah. So like density and refractive, they're numbered values. It's a number that you get as opposed to it being categorical.
So you're talking about this example here, like
yeah.
for the. So I mean, I think that there is two things, right? So if you wanted to treat that as a regression problem, it means that you would have some glasses for which you know their density, and you want to train a model that can predict the refractive index, for example. If you want to train a model that will take as an input the density and will try to predict the refractive index. So in that case, that would be a regression problem. If you think that the density is enough to predict the refractive index, then you can train a model to do that. That's going to be a regression problem. But if you think that the density is not enough to tell you what the refractive index is, if your goal is not to do that, if your goal is just you have a list of glasses, you know their density, you know their refractive index, and you want to see among the glasses that you have, are there groups of glasses that seems to behave similarly to each other? Or do I have one glass that seems to be completely off, which I should double check, like a potential outlier? If this is your objective, then you would use unsupervised learning. So it's more a matter of what do you want to accomplish. If you want to predict something, then you need to use supervised learning. If you do not want to predict something, if you do not want to predict a number, you just want to take some data, group them together, then you would use unsupervised learning. Does it make sense?
Yeah, that makes sense. Thank you.
So yeah, I mean, maybe let me take another example that is outside glasses. Like let's assume that you have you are a store owner, and you have some customer that comes to you. That those customer they buy different things, and you want to think about your customer, and you want to group them. You want to think about, I have different types of customer. I want to group them into different groups of customer that seems to behave similarly to each other. And so if you do that, then it can be useful for you to do, I don't know, some marketing, like to target certain types of customer, etc. But you do not know what those categories are. You do not know that you have customers that would be young or would be rich or would be poor. You do not know anything about this. All you know is you have some customers, they buy stuff into your store, but you do not know anything about them. You just want to group them into groups of customers that look like each other. Then what you would do is that you would look at your customer, you look at what they buy, and based on what they buy, you try to find some patterns. You try to find some groups of customers that look like they buy the same thing. In that case, that would be an unsupervised learning problem. You just try to, you take some data and you look at which data points look similar to each other, but you're not trying to predict anything. You're just trying to group customer together into customers that look similar to each other. So that's an example of unsupervised learning. That's typically how unsupervised learning is used by companies, is just to group things together. By grouping things together, you can learn something. You can learn some patterns of, let's say, customers that seems to behave similarly, or glasses that, again, seems to be similar to each other. But you're just grouping things. You are not trying to predict anything. So that's unsupervised learning. But usually you never have to choose between supervised or unsupervised because they do different things. So if you want to predict something, you will use supervised. If you want to group things, find some clusters, then you will use unsupervised. They are not really competing against each other. They just, it depends on the data that you have. If you have data that do not have any label, then you only use unsupervised. And it depends on what's your objective. What do you want to accomplish with that? Does it make sense? Any other questions regarding the unsupervised and supervised learning? Okay, so let's move to the last type of supervised learning that we haven't talked about yet, which is the case of regression. So what we talked here is supervised learning, where you want to predict a category. You want to predict, does it crystallize or does it vitrify? So now let's talk about the last case, which is supervised learning, but this time's regression. Regression is when you want to predict something. So you have a label, but you want to predict a number. You don't want to predict a category. So in this case, for example, the typical example is that you would have some glasses and you know their composition. So here I'm just going to draw something with 2 dimensions. So let's assume that, for example, you have some sodium silicate glasses. So you have a groups of glasses with different fraction of sodium, and the rest is silica. So just some binary sodium silicate glasses. And in that case, you know how much sodium those glasses have, how much sodium oxide they have. And you are trying to predict something. For example, you're trying to predict the Young's modulus of those glasses. And so in that case, so you have some data points like this. And so your goal in this case is you have some glasses, you know their composition, you have a label, so you know the Young's modulus of those glasses in gigapascal, for example. And in that case, the goal of the regression model will be to build a model to predict the Young's modulus as a function of the composition, right? So in that case, that would be kind of a curve fitting problem where you try to find a curve that maps the input, the composition, and can be used to predict the output. So in that case, the composition would be the input, and the Young's modulus in this case would be the output. So that would be the process of learning. The process of learning would be to find the function or the curve that best maps the composition to the Young's modulus of the glass. And then once you have this, it means that if you have now a new glass with a new amount of sodium oxide, now you become able to predict what would be the Young's modulus of this glass. So that would be the process of now, once you have a model, you can use it to predict what would be the Young's modulus of those glasses. So in that case, that's a regression problem because you have a label. So that's the Young's modulus, that's what you want to predict. And this label is a number. So it's not a category, it's a number that can have any value, like between 2 numbers, you can always find a third number in between, right? So in that case, that's a continuous number. So when you are trying to predict something continuous, now it's a regression problem, not a classification problem. Classification is when you are trying to predict something discrete, for which you only have a few categories. Regression is when you are trying to predict a number that can continuously change. Any questions about that? Okay, so those are basically the three categories, right? So clustering, when you're trying to group the data. Supervised learning is when you're trying to predict something, predict a label. And within supervised, you have either regression when you predict a number, or classification when you're trying to predict a category, a class, a categorical variable, something that is discrete, that can only take a few values. Okay, so now let's talk about some algorithm on how to do that. So I'm going to go back to the case now of clustering. So let's go back to the case of clustering. And so a simple algorithm that you can use to do clustering. So I want to give you a few ideas about a few algorithms that you can use to do those different types of machine learning model that we described. I'm not going to go into too much detail or to review like all the possible algorithms that exist, because there is a very large number, but at least I want to give you some ideas about how it works in practice. So for clustering, for example, a common algorithm is the k-means algorithm. So the k-means algorithm is an algorithm that allows you to take some data and to group them into clusters. So let's come back to the example that we have. So let's assume that you have your glasses, and we're going to use the same example as we had. So let's assume that you know the refractive index and you know the density of those glasses. So you know the refractive index and you know the density of those glasses. And so let's assume that you have the three groups that we discussed previously. So those are three groups of glasses that seem like they behave similarly to each other. So the k-mean algorithm is based on two main steps, or I would say three main steps. The first thing is that in the k-mean algorithm, you will need to decide from the beginning how many clusters do you think you should find in those data. Like for example, here, there is three clusters apparently when you look at those data. But in the k-mean algorithm, this algorithm is not going to tell you how many clusters you have. I mean, it's going to tell you if you want to find three clusters, what are going to be those clusters. So I'll tell you more about this once we start using this cluster in the Orange software in practice. There are some ways to find what is the number of clusters that best describe the data sets. But at least in the basic version of the k-mean algorithm, you have to assume first how many clusters do you intend to find in this data set. So for example, here, let's assume that we think there's going to be three clusters. So in that case, that means that we will assume k equals 3. That means we think there's going to be three different clusters in this data set. So I'll come back to that later, but basically you need to start with that. You need to decide how many clusters do you think there will be. The second step, so after deciding the number of clusters, the second step is that you will place some centroids for those clusters. So the centroids of the cluster, this is going to be the center of each of the cluster. So if you have three clusters, you will need three centroids, C1, C2, C3. And so those centroids are going to be 3 points, and you are going to place those points randomly. So for example, you may say, I have 1 point here, that's going to be C1. You have another point, maybe you will place it here, that's C2. And then you have another point here, that's C3. So you place three centroids randomly within this space. The next step is that you are going to now assign each data point that you have, each of the glass that you have, you will assign it to a centroid. And the way you're going to do that is very simple. You're going to look at for each data point, you are going to look at the distance between a data points and all the centroids, and you are going to take for each data points which centroid is the closer. So for example, let's assume that I'm going to take this data point here. I'm going to calculate the distance between this data point M and the centroid C1. I'm going to calculate the distance between M and the centroid C2 and the distance between M and centroid C3. And based on that, I find that C1 is the closest. So I will assign the point M to the centroid C1. So same thing, like these data points, they are going to be assigned to C1 because C1 is the closest. Next step, those data points here, they are going to be assigned to C2 because all of those data points, C2 is the closest. And the last one, this point is assigned to C3 because C3 is the closest centroid. So that's the next step, is you assign each data point to the closest centroid. So that's the assignment step. Next, you are going to move the centroid. So that's the step number 4, you move the centroid. So how do we move the centroid? Is now we have some preliminary groups of data. So we have the groups of the data points that are red. You have the groups of the data points that are green. You have the groups of the data points that are blue. So let me redraw this thing again. So you have your data points here. And so what you will do is now you will take all the groups of the red points, and you will recalculate what is the new centroid of those red points. So the centroid is the average, right? So if you have those red points, you will calculate what is the average position of all of those red points. That's going to be their new centroid. The centroid is the geometrical average of all of those data points, right? So you calculate what is the new geometrical average of all the red points. So now this centroid has moved from here to here because now you reassign what is the new centroid of these groups of red data points that you have. So same thing, you will do the same for the green. So now you have a group of green points here. You will recalculate the new centroid of this group, which now looks like here. That looks like it's the geometrical average of this of those green points. So it means that you will move the centroid from here to here. Now you have the blue group. This blue group has only 1 point. So in that case, when you have only 1 point, the centroid of this point is the point itself. So you will move the centroid to this position. So now you have moved the centroid. So now you start a new step where you still have the same data points. So I'm going to draw them again here. That's exactly the same data points as before. But now you start a new step where you have the new centroid that have now at a new position. Now you have your centroid C1 that is here. You have the centroid C3 that is here, and you have the centroid C2 that is here. And now you will start looping. So you start looping from the step 3 to step 4. You start reassigning the data points. So now you will say that this data point is a red data point because it's C1 is the closest. So this one, it's also closer to C1 than it is from C2. Those data points, they are still close to C2. So you will you will assign them to the second cluster, and then you have C3, which is assigned to this data point is assigned to C3 because C3 is the closest. So that was step 3. Now you move to step 4. Again, you move the centroid. So now you have some new clusters. You have a new group of red clusters. So you recalculate the centroid of this group of cluster and you move the centroid to the new position. You do the same for the green thing. Now the centroid is probably going to be around there. So you move the centroid to the new position. C3, it's not moving. There's only 1 point, so C3 is not moving. And so as you do that, then gradually you will find that now those points will be assigned to C1 after you move them. And those points will be assigned to C2 after you have moved the centroid to the new position. And so you will repeat those steps 3 and 4. You will assign the data points to the closest centroid and then redetermine the centroid of the groups of data points. And you will do that until the centroids are not moving anymore. At some point, you will reach a step where all of those red data points, they are one centroid, they are one cluster with one centroid, and all the green data points, they are one group with each other, and all the blue data points, they are also one group. And once you have this, then the centroid will not move anymore. As you go from step 3 to step 4, you assign all the data points based on the closest centroid, and then you see if the centroid is changing or not. At some point, you will reach a point where the centroid is not changing. You have a stable case where you have found a group of data points that look close to each other. All the red points are close to each other. All the green points are close to each other. And you have this blue point that looks far away from the other. So that's the idea of the clustering algorithm using k-mean. You just need to start with a given number of clusters, which in this case is 3, and then you iteratively move them by assigning data points to cluster and then moving to the centroid of the new clusters until you reach a stable case where the centroids are not moving anymore. And at this point, it means that you have found your 3 clusters. So the advantage of this is that it's a very simple algorithm and it works pretty well. It will find you the best clusters in the data that you have. The disadvantage of this is that you have to decide from the beginning how many clusters do you think you will find. So because that's going to give you the number of centroids that you place randomly at the beginning. So here we would have to say, I want 3 clusters. If you say from the beginning that I want 2 clusters or I want 4 clusters, then it's going to find 2 clusters or it's going to find 4 clusters. It won't tell you directly what is the best number of clusters that define that can describe the data that you have. So we are once we start to put that into practice, I will still show you how you can in practice find what's the best number of cluster to define a group of data. But at least in this algorithm, in the direct implementation of this algorithm, you have to know from the beginning how many clusters you think you will find in the data. Any questions about this so far?
So does that mean this is similar to like product component analysis?
So you mean the principal component analysis?
Oh, sorry, that was it, principal, yeah.
Mm-hmm. So it's something a little bit different. So the principal component analysis is another example of an unsupervised technique, because in this case, you just have some groups of data and you try to find what are the most influential direction to describe this data, right? So just going to show you a brief example of that. So now we talked about PCA, so the principal component analysis. So in this case, so let's assume that you have some glasses, and let's assume that you know how much sodium you have and how much calcium you have. And so let's assume that you have your glasses like this. So again, that's an unsupervised learning problem because you don't know anything about those glasses. You just have data points of glasses for which you know their composition. You know how much calcium they have, how much sodium they have. What the principal component analysis can do is to find what are the best directions to describe those data. So for example, in this case, what the PCA analysis would do is to tell that there is one direction here that describe the data very well. If you just look at along this axis, then you can look, it can describe the variability of the data very well. And then in that case, you just need, if you want to consider how those data, or how the glasses deviate from this axis that you have defined, then you would consider like this second axis here. So basically what the principal axis does is to transform the variable that you have into a new coordinate system that is better adapted to your data, that better describe the variation of your data. So it would say that there is this, for example, this axis PC1 that looks like it's really aligned with the direction along which you have some variability in your data. And then you have this direction PC2 that looks like it's well, it's orthogonal to PC1. So it's capturing the whatever is not captured by PC1 is going to be captured by PC2. And so in this case, what it does is not to really group data points that are similar to each other like you would have in the clustering. It just finds what are the best axes to describe your data points. So it's in the same category, right? It's also an unsupervised learning analysis, but it doesn't do the same thing as a clustering, right? It just look at what are the best axes to describe the variability of the data points that you have, but it's not going to really group them into different clusters. Does it make sense?
Yes, thank you.
Okay. Any other questions about unsupervised learning? Okay, so we'll come back to that because we will see how to implement in practice this k-mean algorithm in the Orange software. Okay, so let me go back to the PowerPoint. Another example of algorithm that is pretty simple to understand, and in that case, that would be an algorithm for classification. So a supervised algorithm where you have some data points and you want to predict something. You want to predict a category. So in this case, let's assume that you want to predict your living work, and you want to have a model that's tell you to predict whether you should walk back to work or take the bus. So you want something that's going to make a decision for you. And in this case, so you will have certain features that describe the current condition. For example, you will have 3 features. What's the weather like? Is it sunny? Is it raining, or is it cloudy? That's one feature. So that's one input. You will look at the weather. That's going to be one input. You will look at how much time do you have before whatever is your next commitment. How much time do I have before the next thing I have to do? That's going to be the second feature. And you have another feature, which is, are you hungry right now or not? So that's the next feature. So you have those features. Some of those features are categorical. For example, the weather, it's either sunny, either cloudy, or either it's raining. So like this is something that is a categorical variable that can only have a limited number of possible choices. You have some variables that are actually numerical. For example, how much time do you have? This is going to be a number. Like maybe you have like 15 minutes before your next meeting or something like that. So in that case, that's going to be a number. And so your goal is based on those features. So feature number 1, the weather. Feature number 2, how much time do I have? Feature number 3, am I hungry or not, which would be another example of a categorical feature. Based on those three features, you want to train a model that will tell you, should I take the bus or should I walk back home? And so in that case, one of the possible models that you can train in that case would be a decision tree model. The decision tree, as its name suggests, it's going to build a tree with some branches where you will have, you will look at the value of the features, and based on the value of the features, you will go through certain branches. So for example, let's assume that you want to have this model that will tell you, should I take the bus or should I walk? Maybe the most influential feature that's really going to dictate whether you want to walk or if you want to take the bus is going to be the weather. If it's raining, then you will take the bus. So that's going to be, in that case, a very strong choice. Like if it's raining, you know that it doesn't matter how much time you have, it doesn't matter if you're hungry or not, you will take the bus. So that's going to be the most important variable. Then if it's sunny or cloudy, where you're not sure yet if you're going to walk or if you're going to take the bus, that will depend on other features. So if it's sunny, then you will say, okay, I'm just going to look at how much time do I have. If I have a lot of time before my next meeting, then I'm going to walk. So in that case, what the tree will do is that it will look at the time and it will say, if the time is larger than the 30 minutes, then I will go through this branch. If the time is larger than 30 minutes, then I will go through this branch and I will decide to walk. So on the other hand, if the time is lower than 30 minutes, then I will take the bus. Then on the other hand, if it's cloudy, then maybe you will want to consider something else. You will want to say, am I hungry or not? So here, I guess that probably doesn't really make sense. Maybe if you are not hungry, then you will walk. And if you are hungry, well, maybe you will want to take the bus so that you can go back home faster. So that would be an example of a tree where you build this tree, where this tree is based on a series of conditions. And based on each condition, you will select which branch you go to. And at the end, you will reach your prediction. You will reach what is your decision at the end of each branch. So in this case, that would be a classification algorithm where the way you would train this is that you would have a list of previous days. Let's assume over the past months, for each day, you track what the weather is, you track how much time you have, you track how hungry you are, and then you track what was your decision. Did you decide to take the bus, or did you decide to walk, or did you decide to, just walk or take the bus? And then, so you have a data set where you have for each day, what was the weather, how much time did you have, were you hungry or not, and did you decide to walk or to take the bus? And once you do that, so you can train your decision tree. And when you train the decision tree, what it's going to do is to try to find first, what are the most influential features that really dictates what was your choice of walking or taking the bus. And then it's going to adjust, it's going to find what are the optimal branches to describe what was your decision process. So it's going to really find what are the optimal threshold. For example, if it finds that a 30 minutes was really the best threshold that governs whether you decided to walk or to take the bus, then it's going to adjust the tree based on that to really best mimic what was your decision process. So this is the idea of a decision tree, is that it's going to look at the data that it have. It's going to look at all the days, what was the weather, how much time did you have, were you hungry or not, and did you decide to walk or to take the bus? And it's going to try to give you what were the rules behind this decision process. So here, this is a good example of a machine learning model. And this is a good example of the fact that a machine learning model, it takes as input some data, And as output, it gives you some rules. Like for example, in this case, like this decision tree, this is the output of the machine learning model. This machine learning model tells you as an output what are a list of logical decisions, a list of rules to decide if you should walk or take the bus. So in this case, this is one example of this decision tree, which is an example of model that is actually pretty easy to understand. It's easy to interpret. Most of the machine learning model, most of the time, it's very hard to interpret. But in the case of the decision tree, it's actually very easy to interpret. Like you can just look at it, look at the branches, and try to understand why the machine learning model decided to, how it decided to assign each branch, what were the features that were the most influential. The most influential features they are going to be at the top of the decision tree. And then you can understand like what is the meaning of the threshold, like why did it decide that 30 minutes is a good threshold to dictate whether you will want to walk or take the bus. So that's an example of model that you can use for classification purposes. So for example, in the case of the example that we talked about, like if we have some glasses and you know the melting temperature and you know the glass transition temperature, and your goal is to predict if this melt is going to crystallize or vitrify, you could also try to train these types of decision tree where it would look at the value of the melting temperature and the value of the glass transition temperature. And based on that, you will go to different branches to say whether this glass is likely to form a glass or to crystallize. So that would be a decision tree model that you can use for classification purposes. So the advantage of this decision tree is that it's very easy to understand, but the drawback is that usually it's going to have a limited accuracy because it's still a very simple model. So it's still going to be limited in terms of accuracy. Most of the time, there are some models that are more powerful than that. But it's still a good model to start because it's easy to understand, and it's easy to understand how it works, and it's easy to understand how to interpret the prediction from the model, to understand what were the rules that the machine learning model came up with. Do you have any questions about this decision tree types of model for classification? So a very, I would say, simple improvement that you can do to this algorithm is rather than having a single tree, you can train several trees. You can have an ensemble of trees. And in that case, we would call it a forest. A forest model is when you have several trees. And what you do in this case is that you train different trees that are in parallel to each other. And you have those trees, each of those trees is going to make one prediction. So each of those trees is going to tell you, you should walk or you should take the bus. And then you can have some kind of voting system where if you have most of the trees that predict that you should walk, then it means that the forest is going to tell you that you should walk. Or if you have most of the trees predicting that you should take the bus, then the forest model will tell you that you should take the bus. So a very simple improvement of this algorithm is rather than having a single tree, you have an ensemble of trees that form a forest. And these types of forest model are typically more accurate than a single tree because it's based on, it's more flexible, it can be more complex. All of those trees can predict something different. And at the end, they all vote together as a forest to decide what should be the decision, what should be the prediction from the model. And these types of forest model typically will be able to be more accurate than a single decision tree model. Okay. So if there is no question, let's continue. So let's move to the case of regression. So example of regression, for example, is you have some houses, you know the area of the house, and you want to predict the price of the house. So that would be an example of a regression problem where you know something about the house, its area, and based on that, you want to predict how much this house is going to cost. And so you have some data already. So you have an ensemble of houses for which you know to which price those houses got sold. And based on that, based on those historical data, you can train a model that is going to be, in this case, a regression model, because it's going to be a model that predicts something. And in this case, it predicts a number. It predicts a number in dollars. So that's a regression problem. In the case of glasses, you can think about regression problem as follows. For example, you have some glasses and you know the composition of those glasses. You know how much silica those glasses contain, how much alumina those glasses contain. Those are going to be your two input variables. And based on those input variables, you want to predict an output, which in this case would be the glass transition temperature. And so you have an ensemble of data points here for which you know at the same time the glass composition, and you know like what was the corresponding glass transition temperature. And then based on that, by observing those data, you will train a regression model that can learn how to map the glass composition, how to transform the glass composition into its glass transition temperature. And once you have this, it means that you know now for a new glasses, even if you don't know anything about this glass, you would be able to predict what would be its glass transition temperature. You would be able to make a prediction about, for new glasses, if you only know how much silica you have and how much alumina you have, then you would be able to predict what should be its glass transition temperature. So that's the idea of the regression model. You just try to fit the data. You try to find a relationship between the inputs and the output to be able to build a model that can make some prediction for glasses that you have never seen before. So the most simple regression model that you can think of that you've probably used before is just a simple linear regression or a polynomial regression. Those, even though they are very simple algorithm, they can still be described as a machine learning algorithm. Maybe to some extent, the linear regression is the most simple machine learning algorithm that you can think of. And the idea, again, is that you have some input X, and you want to use this to predict an output Y. In this case, there is only one single input, so it's typically something that is pretty easy to do in that case. But in many cases, you will have a lot of input. Like, for example, for a glass, the potential input can be all its composition, like how much, what's the fraction of each oxides, or what's the fraction of each element. Or you can also have as input the annealing time, the annealing temperature, or the ion exchange treatment, or anything like that. Anything that can change, any degree of freedom that you have can be potentially an input. And then you have the output Y. This is what you are trying to predict about this glass. And same thing, you can either predict one single output, or maybe you want to predict several output at the same time. So then when you do these types of regression, you will need to make some hypothesis about the complexity of the relationship between the input and the output. For example, in the case of a regression like this, you will need to say, I think the relationship between the input and the output is linear. So I think it's a very simple relationship that can be described with a linear relationship. Or I think that the relationship is actually more complex. It's polynomial. It should be described by a quadratic relationship like this. Or I think I should have like an even more complex relationship with like a cubic term. So here you will need to make an assumption about how complex you think the relationship between the input and the output is. So that's something we'll talk more about tomorrow, about how to select what is the right level of complexity that you should use, and how to find this kind of automatically, so that you don't have to make any assumption. But at least in the most basic version of regression, the first step is to look at the data and make an assumption about how complex you think the relationship between the input and the output is. So in that case, for example, you will need to select what you think is the maximum degree. Do you think that the data can be captured well by a degree 1 relationship, or do you need a degree 2 or a degree 3 polynomial to describe the relationship between the input and the output? So that's something we'll talk more about tomorrow, but that's about finding the right level of complexity for your model, which is an important task in machine learning, to find how complex the model should be. When you're talking about here polynomial regression, the complexity is mostly what is the maximum degree that you're willing to consider, degree 1, degree 2, degree 3. But for example, when we will talk tomorrow about some artificial neural network, it's going to be about how many neurons do I need in my network? How many layers do I need in my network? That's going to be what dictates the complexity of the model. So you always need to define, for a machine learning model, you need to define how complex you want this model to be. And that's something that we have some techniques to decide how complex, what is the optimal degree of complexity. And that's something that we will talk more tomorrow. Any questions so far? So what I would like to do before we move to the tutorial is just finish on this regression, because so the reason I'm talking about linear regression here and polynomial regression is because it's the simplest to understand. Of course, if you're going to train some machine learning models in the future, I mean, very often we cannot simply use linear regression or polynomial regression, because those are very simple models that are typically do not really flexible enough to describe data, but it's still simple enough to understand. So I'm just going to take a few minutes to go through the example of linear regression, because it gives some ideas that are pretty generic for machine learning. So the first thing I would like to talk about is, let's assume that you think that your data can be described with a linear relationship. So you have your data like this. So you have an input X and you have an output Y, and you have some data points, and you think a linear relationship is going to be appropriate to describe, to find how to convert the input X into the output Y. So in that case, what you would do is, first you would make an hypothesis. So you would say, I think that I can describe the data with this simple linear model. And in this model, you have two coefficients, theta 1, theta 2. Theta naught is the intercept, and theta 1 is the slope. So those are the two parameters. And in this case, the process of learning is going to be to learn what are the optimal values for those two parameters, theta naught and theta 1. So the process of learning in this case will be, can I find the optimal value of theta 1 and theta naught to describe the relationship between input and output? For this, you need to define a cost function. So this cost function is like a mean square error. It tells you, for a given value of theta 1 and theta naught, for example, if I take like this types of value where theta 1 is obviously larger, you can calculate that. You can calculate how good this assumption is. So you make a given hypothesis. You choose a given value for theta naught and theta 1. Then you calculate the distance between the model that you have and the actual data points. Like for example, here, if you choose a large value of theta 1, you will have a very large distance. What this cost function is, it calculates the mean square error, the mean square difference between your assumption and the actual data points. And it takes the square of this, sum it all, and divide by the number of data points. So this cost function tells you how good your assumption is. And then based on that, your goal is to minimize this cost function. Your goal is to find the value of the parameters theta naught and theta 1 that will minimize the cost function. So that's basically what the process of learning is. You have a cost function and you try to find what are the optimal coefficients that will minimize the cost function. And so one way to think about this, to represent this, is you have this kind of landscape here, where, for example, you will start by an initial choice for theta 1 and theta naught. And then, so that's going to give you a value for your cost function. And your goal, starting from that, is to gradually change the value of theta naught and theta 1 until you can find your minimum of cost function, until you can find how to minimize the difference between the model and the actual data points. And once you have found the minimal difference between your model and the data points, then that's how you know that you have found the optimal value for your parameters here. So that's the process of learning. In any kind of machine learning model, the process of learning is going to be like this. You need to make an assumption. You have some parameters in your model. You define a cost function that captures how good your model is, and then you vary the parameters until you minimize your cost function. And once you have this, then you have found a model where the parameters have been optimized in order to give you the minimum error. Okay, so that's the process of learning, and it's something that is pretty generic to machine learning algorithm. Do you have any questions regarding this? Okay, so if not, I suggest we do the break now, and then after the break we can go back to the tutorial. So can we have a 15-minute break? So we would restart around 11:45 or 11:45 my time, so 12:45 East time. Okay, so let's resume in 15 minutes. So the first thing is, so there was a question in the chat that I missed. Sorry about this. So I just want to come back to that before we move to the tutorial thing. So so what we said here is in the case of linear regression. So let's assume that you have some data, and you have an input and an output y, and you want to find what is the best line that you describe as a function h that is an intercept plus a slope times x. And you want to find, your goal is to find what is the optimal value of those parameters, right? So again, that's a simple example for linear regression, but most machine learning algorithm for regression, it's based on the same idea, is that you have some parameters and you need to optimize those hyperparameters to find the best relationship between the input and the output. So the way you do that is that you need to define your cost function. So the cost function is the difference between your model and the actual data points. So you take the difference, the square difference between the actual data points that you have and the prediction from your model, and you calculate the square difference. If your model is very bad like this, then you get a high cost function. If your model is good like this, then you will get a low cost function. So then the last question is, you need to try to find the best value of the parameters to minimize the cost function. So you can think about this as follow, is that you have your cost function. Your cost function is going to be something like this, where you need to find the best value of the parameters, theta naught and theta 1. And initially, you will start with the wrong value for theta naught and theta 1. And you will want to see how should I change theta naught and theta 1 in order to minimize the cost function. And so the question in the chat was, can you always minimize? Can you always find the minimum of this cost function? And so the answer is not always. So when you are doing linear regression or polynomial regression, the good thing is that your cost function is always going to be like this. It's always going to be a convex function like this. And in that case, it is easy to minimize because all you can do is start with an initial value for the parameters, and then you can calculate the derivative of the cost function with respect to the parameter. So the gradient, you can calculate if I increase theta or if I decrease theta, is it going to increase the cost function or decrease the cost function? So that's the derivative of the cost function with respect to the parameter. And based on this derivative, based on this gradient, you can say that if you find that the derivative is positive, it means that if you increase theta, the cost function is going to increase. Then in that case, you will want to decrease theta to go towards the direction of minimizing the cost function. And in that case, you will want to decrease theta, recalculate the new cost function, decrease theta again, recalculate the new cost function until you find the minimum. So in the case of a linear regression, you will always find the minimum if you just decrease theta whenever the derivative of the cost function with respect to theta is positive. And if you are in a case where now the derivative is negative, so the derivative of the cost function with respect to theta is negative, then you will want to do the opposite. You will want to increase theta to go towards the direction where the cost function is decreasing. So this is what happened in the case of linear regression. In that case, it always works. But for a more complex model, there is a risk that your cost function can be like this. This is the cost function with respect to the parameters of your model. And then the problem with that is that if you start with there, then you might get stuck into a local minimum. And then your model would think it has found the best value of the parameters that minimize the cost function, but actually those are not necessarily the best parameters. So this is for more complex machine learning model. You have a chance that your model might not find the optimal parameter. So the one thing that you can try in that case is you can try to retrain your model several times by selecting various initial value for the parameter. So if you retrain your model several times and again you try another starting point for the initial value of the parameter, and then you try a third time and you do the same minimization several times. If you repeat that enough time, then at some point you will get lucky and find the real minimum, the real value of the parameters that really minimize the difference between your model and the actual data point. So this problem can be solved by repeating the training of your model several times, but it's something that is a little bit time consuming. But still, in practice, most machine learning models are not really affected by that. And it's something that, despite the fact that you have a risk to get stuck into local minima, in practice, that's not really a problem. In practice, most of the time, you can still find some good value for your parameter, despite the fact that your model might still get stuck into a local minimum like this. So that's something we will see when we use this in practice for with the Orange software. In theory, you have this risk of getting stuck in local minima, so that you would not be able to find the best value for the parameters. But in practice, this is rarely the case. In practice, very often, you will find good parameters and you will be able to find a good model that can describe well your data. Does it? I hope it answered the question in the chat. So if there is no more question, let's move back to Orange. And what we are going to do is first, let me ask you if one of you had, so what we tried to do yesterday is to try to consider a data set of calcium aluminosilicate glasses, a data set for which you have several calcium aluminosilicate glasses, and you wanted to find a new feature that can best describe the data points, that can best describe the modulus of those glasses. So does one of you has like an idea of what could be a good feature that that best describe the modulus of those glasses?
Yeah, I think I found it, Professor.
Mm-hmm.
So I believe it is alumina minus calcium, all divided by silica.
Yeah, so I think that can be a good idea. So let me so what was your rationale behind this? Like, why do you think these types of metrics would be a good feature to describe the Young's modulus of those glasses?
Well, it's what I do every day. I guess I just have a lot of experience with these oxides and knowing what they do to modulus. But you can see it in the data too. If you look at the table of data, you can sort of get an idea that, you know, calcium is not really great for modulus. Alumina is really positive for modulus, and silica is just sort of there because it has to be there.
Mm-hmm. Yeah. Okay, so that sounds good. I think that's a great example of how you can use your previous experience to find features that you think are going to be useful at predicting glass properties. So let me show you what I think could have been another alternative approach that gives pretty much the same results, but with a slightly different viewpoint on this. So like what I'm going to briefly show you here is what the kind of features you can come up with if you know a little bit about the atomic structure of those glasses, right? So we're talking about those calcium aluminosilicate glasses. And so if you know a little bit about those glasses, right? So their structure is that each silicon is surrounded by 4 oxygen. And if you have pure silica, then all of those oxygen atoms are what we call bridging oxygen. So those are oxygen that are connected to 2 network forming atoms. And starting from there, so there is two things that can happen. The first thing is that calcium is going to create some non-bridging oxygen. So if you add calcium to that, calcium is going to break some bonds between the silicon atoms. So starting from a situation where in pure silica, all the oxygen were bridging oxygen like this, where each oxygen is linking to silicon atoms. In this, when you add some calcium, you create those non-bridging oxygen that are some oxygen that are connected to now only 1 silicon atom. So when you do that, so you create those non-bridging oxygen, NBO, and usually those non-bridging oxygen, they tend to weaken the glass. They tend to make the glass more flexible or less rigid. So it will tend to decrease the modulus of the glasses. And then on the other hand, when you add aluminum, that's kind of the opposite effect. When you add aluminum, you will decrease the number of non-bridging oxygen, because in the case of aluminum, again, so this is assuming you know a little bit about glass chemistry, but in the case of aluminum, the aluminum will use a calcium to compensate its charge. So I'm not going to go into too much detail about this because I don't want to spend too much time on glass chemistry, but the idea is that every time you add an aluminum, it's going to use the calcium to compensate its charge. And then it means that the calcium is not used to create non-bridging oxygen anymore. So a useful feature that can be defined is that you can use the following rule. Each calcium will create 2 non-bridging oxygen. So every time you add 1 calcium, you will create those 2 non-bridging oxygen. And on the other hand, each aluminum will consume 1 non-bridging oxygen. Every time you add 1 aluminum, it's going to remove 1 non-bridging oxygen in the glass. So based on this, a useful feature that you can calculate is how many of the non-bridging oxygen do you have? And so this number of non-bridging oxygen is given by how much calcium you have. Every time you add 1 mole of calcium oxide, you will add 1 mole of non-bridging oxygen. But every time you add, since each calcium creates 2 non-bridging oxygen, you need to add a factor 2 here. Every time you add 1 mole of calcium oxides, you will create 2 mole of non-bridging oxygen. But on the other hand, every time you add some alumina, some Al2O3, each aluminum will create 1 non-bridging oxygen. So every time you have 1 mole of Al2O3, it's going to create 2 mole of NBO, because you have 2 aluminum per mole of alumina, per mole of Al2O3. So in that case, a useful feature would be to look at this, which is actually the kind of the same thing that you mentioned. It's just basically taking the difference between calcium and alumina. Another feature that is also useful is the number of non-bridging oxygen per tetrahedron, which is actually what you mentioned. So in that case, you would just take the number of non-bridging oxygen and divide it by the number of tetrahedral atoms that you have. So for example, here, so you have the number of non-bridging oxygen is CaO minus Al2O3, and you divide by the number of tetrahedral atoms, which can be either silica or alumina. So aluminum or silicon, those are 2 types of tetrahedral atoms. And so usually this metric, the number of non-bridging oxygen per tetrahedron, is a good metric to define how depolymerized the glass is. So let's see what it looks like. So I just want to show you briefly that, because it's more about illustrating how we create new features. So let's go back to Orange. So the idea is as follows. So you look at this. So far you have your output, which is the Young's modulus, and then you have the input, which is calcium, alumina, silica. And so none of those inputs are very influential on their own. Like there is not a very good relationship between this input and the output. So what you would do is that you would create a new feature. So you use the feature constructor. So let's assume, for example, that we are going to use this alumina, this metric that I defined here, the number of non-bridging oxygen divided by the number of tetrahedrons. So you use the formula that I just described on the iPad. You take the number of calcium oxide, each calcium oxide will create 2 NBO. Then each aluminum atom will remove 1 NBO. So this thing is the number of NBO, the number of non-bridging oxygen. And then you divide by the number of tetrahedral atom, the number of silicon, plus the number of aluminum. Here there is a factor 2 because every time you have 1 mole of Al2O3, you have 2 mole of aluminum. And then you create this new features. So it's a new feature that is a mathematical function of the initial features that you had, which were CaO, Al2O3, and SiO2. So now that creates a new feature in your pipeline, in your workflow, and you can now use this feature. Is going to be transmitted to the whatever comes to the right of this widget. So now, for example, if we plot again, we make a new plot, and now we plot the Young's modulus as a function of this new feature, this NBO over T. Now you have a much stronger relationship because the Young's modulus is very related to this NBO over T metric. The more non-bridging oxygen you have, the lower the modulus become. So that's an example here of within this software, how you can create new features, new mathematical transformation of the variable that you have to create new features that either based on your experience or based on your knowledge of the physics or chemistry of glasses, you think are going to be good features that can be influential to predict glass properties. Okay, so of course you could have found other features that probably would have worked well, but at least this this feature about the non-bridging oxygen is probably a good example that is very often going to be correlated to the modulus of glasses. Do you have any questions about this? So here, for example, at this point, like if you want to, you can save, now that you have created these new features, you could save it. So you can use the widget save data and then say, I'm going to save this. And what it's going to do is to create a new Excel file where you would be able to find in this Excel file the new features that you created. So now you will have this new Excel file where now you have this new variable NBO over T that you created with this feature construction widget. Okay. Okay. Any questions about this before we move to using this to implement a machine learning model? Okay, so now what we are going to see is how we can use this orange to first try to do a clustering model. So we are going to start with the case of unsupervised learning. And what I want to show you is how you can use this orange software to implement a k-mean algorithm. So for this, I'm going to start by just kind of drawing some fake data just to show you how the k-mean algorithm works. And then same as yesterday, I'm going to send you an actual database of glasses. And then I will ask you to look into that and to see whether you can look into those glasses and find some groups of glasses that are similar to each other by using the k-mean clustering algorithm. So let's take an example. So here, rather than loading an actual Excel file, I'm just going to draw some data points. So I'm going to use the paint data widget. So here, I'm going to just draw some points and I'm going to draw different clusters. So I'm going to draw one cluster here, another cluster here, and another cluster here. So here, the assumption is that the model should be able to find 3 clusters. That's what we expect. So if you want to use unsupervised learning, one thing that is useful to do is always first to visualize the data. So we can start with that. So I can create a scatter plot And here it's unsupervised. So I do not know any label. I only know some variable X and Y. I can look at the data, and here it's pretty obvious that I have 3 clusters, but sometimes it's very hard to see that if you have more than 2 dimensions. If you have a lot of dimension, it's very hard to appreciate how many clusters do you have. So that's one thing. I can also, one thing that is very useful for unsupervised analysis is to calculate the distance between all the points. So one thing I can do is for each pair of those points, I can calculate the distance between all the pairs of points. So let me show you how it looks like. So I would draw a line starting from those data widget, and I'm going to define a new widget, which is the distances. What this distance widget does is that it's going to calculate for each pair of data points, it's going to calculate the distance between those 2 data points. So what it does is just it's calculate the Euclidean distance between the pairs of data points. So it's going to take for each data point, each pair of data point, it's going to calculate just the distance, the Euclidean distance between each pair of data points. So let's see what it looks like. I'm going to show you, we can use something which is called the distance map. Distance map is something that you can use to visualize this distance. So let me show you what it looks like. Here, you get some kind of matrix where each line of the matrix is one glass, and each column of the matrix is also another glass. So each line is 1 data point. Each column is also 1 data point. And then you have this matrix where for each pixel of this matrix, it's going to show you the distance between those 2 data points. So for example, here, if you take all this diagonal line here, those distances would be always 0, because that would be the distance between 1 point and the same point. So if you take the distance between 1 point and the same point, then the distance would be 0, because it's just 2 times the same point. And every time you look at a pixel that is not on the y equal x line here, then it's going to be the distance between data point number 1 with another data point. It's going to give you the distance. So why is this useful to do that? Because if I look at this map, I can clearly see that there is several groups of data. There is clearly 3 main groups of data. There is, when you look at the distance, here, if I take this group of data points, there is another group of data points here for which they have a very low distance. So a distance close to 0, while on the other hand, the distance with all the groups of data points is very high. It's more like a yellow color, which means that it's a high distance. And now you find here that there is 3 squares, 3 big squares of groups of data points that are close to each other. So that's another way to look into the fact that there seem to be 3 groups of data points that have distance that are pretty close. They are pretty close to each other. So that's another visualization. The advantage of this is that even if you have a lot of features, you can still just calculate the distance between all of those glasses, and that gives you a map that you can try to understand as a human. Like if you look at this map here, you can directly see some groups of data points that looks like they have a distance that is close to each other. And here, like we clearly see 3 groups that are close to each other and that are far away from other groups. Like if you take group number 1, it's close to the other point in the group number 1, but it's far from group number 2, and it's far from group number 3. So that's something that is always useful to do, is to draw this distance map for unsupervised learning problem. So now what we're going to do is just to train this K-mean algorithm. So what I'm going to do is to, again, you start from the data, and now you are going to define a new widget, which is the K-mean widget. And this K-means is going to do exactly what I told you before. It's going to try to apply the clustering algorithm by first putting some centroids and then moving those centroids by assigning data points to each cluster and then moving the centroids to the centroids of each of the groups, and do that iteratively until the centroids do not move anymore. So if we click on that, the first thing that you need to decide is how many centroids do you want to consider? How many clusters do you consider? Do you find that you should? Do you think you should find? So here I have 3 because I know I should find 3 clusters. But if you do not know, then maybe you would put 2 clusters. So let's start with 2 clusters. Let's assume that we do not know how many clusters we should have. Then, for example, we would start with k equal 2. So let's assume that we want to find 2 clusters. So what this algorithm is going to do is to take the data and to find what are the best 2 clusters that describe this data. So then after that, everything that comes after that, the data would have been clustered. So I can create a new plot like this. So I create a new scatter plot. And now I will be able to see what is the outcome of the clustering. So the way I can do that is, so first you need to choose the axis. So I'm still going to use X and Y, that's the 2 axes. It tells you the position of each data points. But now what I can do is I can assign a different color to the different cluster that have been found by K-mean. So here, I said I want 2 clusters. So K-mean, it found 2 clusters. One is the blue cluster, C1. One is the red cluster, C2. So in this case, K-mean, we asked for 2 clusters. So it found 2 clusters. So, and those clusters, I guess, kind of make sense, even though this one should clearly be 2 different clusters. It should not be just one single cluster. So now what we can do is, one of the good things about this orange thing is that you can dynamically change the parameter of K-mean and see how this plot is going to be dynamically changed. So for example, here, now if I increase the number of clusters, so now I say, I want to find 3 clusters. Now K-mean is going to redo this analysis and is going to try to find what are the 3 best clusters. And so now it finds that those 3 groups of data points are the 3 best clusters, right? So which is what we expect. So in this case, 3 is the number of clusters that make sense. If I say I want to find 4 clusters, let's see what it finds. So here, if I want to find 4 clusters, what it actually does is that it's going to find this as cluster 1, this as cluster 2, and then it finds like it divides this cluster into a series of 2 subclusters, this orange cluster and this red cluster. And in this case, again, this is just because you said you wanted 4 clusters, so it found 4 clusters. So just because this is what you ask, and K-mean cannot guess on its own how many clusters there is in the data set. So that being said, so there is still a way for you to find what is the optimal number of clusters. And for this, one thing you can do is to try different combinations. So you can run the K-mean algorithm with 2 clusters, then 3 clusters, then 4 clusters, then 5 clusters, etc. And then you can see how good the clustering was. And one of the things that you can calculate to do that is to calculate the silhouette. So the silhouette is a property that tells you how good the clustering analysis is. So I'm not going to go into too much detail on how you calculate the silhouette, but basically the silhouette is a number. It's like a score that goes between -1 to +1. And the higher is the silhouette score, the better is the quality of the clustering. So here, let's assume that we do not know what is the optimal number of clusters to describe those data points. One thing you can do is that you can use this function here. You can say, I want to try every combination between 2 clusters up to 5 clusters. And so what this orange software is going to do is that it's going to try to use 2 clusters or 3 clusters or 4 clusters or 5 clusters. And you see, every time I'm choosing a different one, it's going to dynamically change the prediction. For example, if I say 5 clusters, find this blue one, this orange one, this red one, this yellow one, and it's green one. And then it's going to calculate the silhouette score for each cluster. And for example, here you can see that the silhouette is maximum for when the number of clusters equal 3. This means that in this case, a number of clusters of 3 is the best, it's the most optimal number of clusters that gives you the best clustering analysis at the end. So that's one way when you don't know the number of clusters, is to do this analysis by trying k equal 2, k equal 3, k equal 4, like trying different number of clusters. For each number of clusters, you calculate the silhouette, and then you select the number of clusters that gives you the highest silhouette score. And that gives you an idea of what is the best number of clusters that best describe your data set. Does it make sense so far to everybody? So what I'm going to do now is I'm going to send you a data set that, again, I'm going to put it in the chat. And what I would like you to do is to load this this data set, to download it, and to find some clusters of glasses. So let me show you how it looks. So I'm going to put this data set in the chat. So same as yesterday. So I gave the address in the chat. You can either download the dataset to your computer, and maybe you should do that if you want to make sure you keep it, or you can directly load this dataset by using the file widget and then putting here the URL of the that I just gave you in the chat. So let me show you what this dataset looks like. So this dataset, what it contains looks like this. So you have a series of glass composition where you have, in this case, 60 glasses. And for each of those glasses, you know how much silica, how much alumina, how much sodium, how much calcium it contains. And those are the mole fraction for each case. And so those things, they always add up to 100%. So it's always going to be, the sum always going to be 100%. So you get the mole fraction of each of those glasses, for each oxide within those glasses. And what we want to find is, within those glasses, so some of them you will see have a higher amount of silica, some of them have a lower amount of silica, etc. So those glasses, we want to see whether we can group them. We want to see whether, by looking at those data sets, at all those glasses, can we find some groups of glasses that look similar to each other? And the idea is that if we do that, then we can find groups of glasses that most likely belong to different families of glasses. So some of them might be window glasses, some of them might be something else, but we do not know that. We do not have any label about those glasses. So only thing we know is their composition, and we want to group them into groups of glasses, right? So what I would like you to do is to load this data to Orange. So in this case, if you try to load them, you will need to look at so you have 4 columns in these assets. You will say that all of them are numeric. And in this case, all of them are features. There is no target because it's an unsupervised learning problem. There is no target. There's nothing that you're trying to predict. And then, so same thing. So now you have this data. You can plot it if you want to see what it looks like. So for example, here, if I plot the sodium on the x-axis and the calcium on the y-axis, it looks like there are 3 groups of data points. Some of them have a lot of sodium and very little calcium. Some of them have a lot of calcium and very little sodium. And some of them have a mixture of sodium and calcium. So it looks like there's going to be 3 groups of glasses here. But now it's a bit harder to see because it depends on the variable that you choose. For example, if you choose other variables, like if you choose, for example, if you plot data where you put how much silica they have on the x-axis and how much alumina they have on the y-axis, then already it becomes a little bit less clear. You have one data point here that is a little bit isolated. So like you have all of those variables here. You have like 4 different inputs. So it becomes harder to group the data points together when you have more than just 2 inputs. Okay, so what I would like you to do is to consider this data set and see, to do a k-mean algorithm analysis to group them into clusters, and to tell me how many clusters you think best describe this data set. And then maybe at the end, you can tell me what you think those 3 groups of glasses correspond to. So let me show you a little bit like the list of instruction that I have in mind for this. Yeah, so what I have in mind is the following here. So for the clustering is that, so you would load the data set, you can visualize the data, train the k-means algorithm, and then find what is the best number of clusters that best describe the data set. Okay, so did everybody manage to download the data set that I put in the chat? Okay, so I'll leave you a few minutes to think about this. If you have questions, now is the time. I think it's better if we make it more like a discussion from this point rather than just you listening to me. So if you have either some preliminary results about how many clusters you think is the best, or if you have questions or anything like that about these data sets, now we can discuss about it. So what I would suggest you to do, besides what is written here, is every time you get some new data, you should try to visualize it. So you can plot one variable as a function of the other. You can plot the distribution of each of the variables. That's always useful to do that. You can do like what we did with the first example. You can plot the distance between each of the data points, because that's going to be helpful for you to have a first ideas of how many clusters, how many groups of data points appear to be having a small distance with respect to each other. And then you can try to do this clustering k-means algorithm, try different values of k and see which one gives you the highest silhouette score. And then based on that, see what are the clusters that are actually found by the algorithm, and see whether it makes sense to you, whether those clusters do seem meaningful to you. Any questions regarding this, or does anybody already have an answer about how many clusters is the best in this case? Okay, so somebody found 3 clusters, which makes sense. Okay, so it looks like several of you got free clusters. So let me show you a little bit just to make sure everybody's on the same page, right? So the first thing you can do again is, for example, calculate the distance, then making a distance map. And again, if you do that, you find that there appears to be three groups that are blue. So three groups with a low distance from each other. And those three groups have a high distance that with a yellow color when it's the distance between glasses that belongs to different groups. So that's the first indication that there seems to be three groups. So then we'll start the k-mean algorithm, and we are going to make some plots to see what kind of clustering is done. So again, you can say, I want to try different value of.
Can I see your screen?
Oh, let me share again, sorry. Sorry, can you see it now?
Yeah, thanks.
Let me restart that just to make sure you could see what I was talking about. So step one, you calculate the distance between all the data points and you make a map. So this is where you see three groups of data points that appear to have a low distance from each other. So three groups where the distance between members of this group is blue. So low distance, but very yellow in between glasses belonging to different groups. So that's the first indication that there might be three groups, right? So now let's do the same thing. So let's do the k-mean analysis. I'm going to say, I want to try different values of clusters ranging from 5 to 2, so from 2 to 5. So here we can already see that a number of clusters of 3 gives you the highest silhouette. Let's see what kind of clustering is actually performed. So for this, I'm plotting the glasses. So you can choose different you can choose different axes. You can choose like to plot things with AL203 on the x-axis and SiO2 on the y-axis. If you do not know what is the best variables to use, one thing you can do is to use this option called fine informative projection. So when you do that, what Orange is going to do is to tell you what it thinks are the best variable to look at your data. And for example, here, it's telling you that using CAO on the x-axis and SiO2 on the y-axis is a good way to separate the data. So when you look at this, I mean, it doesn't really seem very obvious that is the best way, but it does look like when you look at it like this, you have 3 groups, 2 groups with high silica content, and 1 group here with low silica content. I think maybe still using those two variables with calcium oxide and on the x-axis and sodium on the y-axis is probably still a clear representation in this case. So now let's see what kind of clustering has been done, for which I can assign the color of each data point based on the cluster that was found by Orange, right? So again, we can do the same thing as we did. If we say I want 2 clusters, then what Orange does, what the k-mean algorithm is to find 1 blue cluster here, which is the group of glasses that have a lot of sodium but very little calcium. And then you have another group, which it just put them together into the same cluster. This is because you said I only want 2 clusters. On the other hand, if you say I want 5 clusters, then it's going to create it's going to take this cluster and divide it into a series of subclusters. when you look into that here, it's not clear why the yellow are grouped together while the orange are grouped together. But remember that this is only one variable here. We are just looking at Na2O and CaO. But maybe if we look at other variable, like for example, now if we look at SiO2, now it's clear that the orange one are the one that have really low silica, and the yellow one are the one that have a little bit more silica. So when you look at different variables, you can try to make more sense about why the clustering algorithm found the cluster that it has found. But still, in this case, the best number of clusters is 3. So when you have 3 clusters, that's where you have the highest silhouette. And you find here those 3 groups of data points where you have the cluster 1. Let me remove that. The blue cluster that is high sodium and low silica. Then you have a second cluster, which is medium sodium, intermediate sodium and high silica. And then you have a last group, which is almost no sodium and high silica content. So clearly here, 3 clusters look like it's the most optimal clustering analysis for those glasses. One thing you can do if you want is you can, for example, define a new widget here, which is a data table. And now what it's going to do is that it's going to show you, you still have the same glasses here with the glass composition. And it's going to tell you which cluster is assigned to each glass. So like you have cluster C1, C2, and C3 for each of those glasses. And for example, if you want to export this, you can say, I want to save this. And it's gonna, you will be able to save a file where you have the information of, for each of the glasses, which cluster it belongs to, okay? So maybe let me ask you a question before we move to another example. Like here, like we have a 3 cluster, like any idea about like roughly what type of family of glasses those 3 families correspond to? Like you have 3 clusters here. Remember that it's an unsupervised cases. So we do not have any label. We just group the data that look similar to each other. But now that we have those 3 groups, like, do you have any idea what those 3 groups of glasses roughly correspond to? What types of glasses or what type of application would those glasses be used for? Any idea? So for example, like one category of those glasses would be some window glasses, right? So you, those glasses, they are all aluminosilicate, right? So all of those glasses contain some aluminum, some silica, some sodium, and some calcium. But roughly, there is 3 main group of glasses, at least in this data set, right? So one are the red points here. Those red points, if I look at it in terms of sodium and calcium, these red points are the group of glasses that contains about, let's say, 15% of sodium oxide and about 10% of calcium oxide. So those would be some typical window glasses. Another way of seeing that is that if you look at SiO2 and Al2O3, those are the ones that do not contain so much aluminum. So those are some typical soda-lime silicate glasses that do not contain aluminum, right? Some typical window glasses. So this is one group that was found by the clustering. Then you have another group here. For example, let's say the blue group. The blue group contains more alumina. So if we look in more detail at, for example, silica on the x-axis and sodium on the x-axis, this blue group would be a group of glasses that contain a lot of sodium and some silica and also some alumina. And on the other hand, if we look at calcium oxide, very little calcium oxide. So this would be a group of glasses that is more like a display glasses, like the group of glasses that is used for substrate for OLED glasses that, sorry, let me take it back. this is a group of glasses that contain very little calcium. So it's actually more like a cover glass. So this is a group of glasses that contain some silica, some alumina, and some sodium. So this is some glasses that can be used for ion exchange, for example, for like a typical gorilla glass, like just some sodium aluminosilicate glasses, basically. And then you have the last group of glasses, which is this red glasses. It contains some silica, sorry, so I'm getting tired. The last group is this green glasses. The green group of glasses contains a lot of silica, basically contains very little sodium. If we look in terms of alumina, it contains some aluminum and it contains some calcium. So if you look at this green, it contains some calcium, contains some aluminum, contains some silica, but doesn't contain so much sodium. So those would be some display glasses, some substrate glasses that are used for OLED substrate that contains no sodium or very little sodium in them. Okay, so anyway, this is more like some interpretation, but basically here the idea is that even if you do not know anything about those glasses, using this clustering, you can just group them and find those three families of glasses in a completely unsupervised fashion without knowing anything about those glasses, just by looking at which types of glasses look similar to each other. Any questions about this? Okay, so if there is no question, so let's move to now a classification problem. So I'm going to start by showing an example by drawing some data again, and then I'll give you a file to download and play with. So in this case, so let me draw some data first to illustrate. So in this case, it's a classification problem, which means that we will want to predict for different glasses. We will know which family they belong to. And this time we want to predict a model that can say, for this glass composition, it's a window glass, or for this glass composition, it's a cover glass, or it's a display glass, or it's a bioactive glasses, or things like that. So in this case, it's different because we already have a data set for glasses for which we know their composition and the class they belong to. So if I want to do this, like for the sake of illustration, I'm going to draw some points here. Those are some points for which you know two features, you know X and you know Y. Those two X and Y can be, for example, how much calcium oxide and how much sodium oxide those glass contain. But now the difference is that you also know two families of glasses. You know which families of glasses those glasses belong to. Before, all those points were black because we have no information about which family they belong to. But now I know that some of those glasses are blue, some of those glasses are red. And I know this information because now it's a case of supervised learning where I already have a label for those glasses. And now, so what we will want to do is to train a model, a classification model that learns how to find the best boundary between those two glasses, those two types of glasses, so that later on you can come up with any glass composition and the model will be able to tell you, I think it's a window glass, or I think it's a cover glass, or I think it's a bioactive glass, or something like that. So now the idea is that you still want to predict for a given glass which groups it belongs to, but this time you have this labeled information already, so you can use this to train a classification algorithm. So let me show you how it looks like before I send you the real data set. So in this case, so this is the data points. I can use it just to plot and see what it looks like. So in this case, I have some points for which I know two features X and Y, and I have their class now. Now I have their class. Before, in the case of unsupervised learning, I did not have any class. So now I have two classes, the blue and the red. And that's what I want to do. I want to train a model that can learn how to predict if a glass is blue or if a glass is red. So for this, let's do that. So I'm going to try now to use a classification model. So for this, you will need to go into the model category. And here you have different types of model available. And so for example, here I'm going to choose a tree model. So this is the same kind of tree model that we discussed before to predict whether you should walk or take the bus to go back home. So here what I'm going to do is to train a tree model that learns whether a glass is red or blue, depending on its composition, depending on the value of X and Y. So if I want to train this model, I just need to connect those two things. And so now this tree model is going to be used to predict whether the glass is blue or red. So here you have a few parameters. I'm not going to go into too much detail, but those are some parameters that dictates how complex the model is, like how many branches, how many leaves do you want in your tree. So those are some parameters that you need to change to decide how complex you want your tree to be. So we'll talk more about this tomorrow, but that's always something important in machine learning, is that you need to decide how complex your model how complex your model should be. So now you have your tree here. So the question is this tree able to accurately predict which glass is blue and which glass is red? So one thing you can do for this is you can visualize what it's predicting. You can test how accurate this model is. So for this, you will need to go to a different category, which is the evaluate. The evaluate category is going to be useful to see how accurate the classification model is. So for example, here I'm going to use the test and score widget. This test and score is going to be useful to tell me how accurate this tree model is. Like this tree model, how good is it at classifying the glasses that are red from the glasses that are blue? So for this, you can connect those two. And here, if you want to compare and see how accurate the model is, what you need to do is to see what the model thinks, whether the model thinks each data point is red or blue, and you need to compare this with you need to compare this with the actual color of the data points, right? So here you have your glasses. They are either blue or red. So if we want to see how accurate the model is, we need to see what is the model predicting for each data points. Is the model predicting that it's red or blue? And then we need to compare with what was the actual color of those data points. So for this, what I'm going to do is to take the test and score here. I'm going to connect it to the true data, and I'm connecting it to the model. So that way, this test and score is going to be able to compare the prediction from the model with the true data that we use to train the model. So let's see what it looks like. So here you have a few options here. I'm not going to talk too much about this because we're going to talk more about this tomorrow. So for now, I'm going to select the option test on trained data. If I select this option test on trained data, what it's going to do is that it's going to use the data that I'm using to train the model. So the data that I just draw here, and it's going to see how accurate the model is at predicting whether each data point is red or blue. And now you can see a few information here. For example, like here, you have the CA. CA is the classification accuracy. So this means that 98% of the time, or close to 99% of the time, the model is able to properly classify a data point into being red or into being blue. So this score here tells you how accurate the model is. So here the model is pretty accurate, but it's not perfect. It's making some errors sometimes. Sometimes it's taking a data point. It thinks this data point should be blue, but actually this data point should be red, or vice versa. So one useful way to understand what the model gets right and what the model gets wrong is to draw something which is called the confusion matrix. The confusion matrix, so again, I can just link it to the test and score and add this widget. What the confusion matrix is going to show you is how good the model is at predicting the color of each data point. So this confusion matrix looks like this. Each line here corresponds to the actual color of each data point. So for example, like here you have the red and the blue data points. And each column, so each line is the actual color of the data points, and each column corresponds to what is the prediction of the model. Each model the model will think that certain data points are red or blue. And so most of the time, the model gets this right. So if you look like here, this box here shows you that if the data points is red, the model will classify it as red 1% of the time. So it means that this is a good accuracy. But on the other hand, if you look at when the point is actually blue, the model will sometimes think it's blue, but it's going to think sometimes it's red. So here, those boxes correspond to the accuracy of the model. So it shows you the comparison between what is the true color and what is predicted. So for example, here, what this model shows is that the model thinks that sometimes it predicts some points to be of the color C1, although the color should be C2. So sometimes the model thinks that a data point should be red, but actually this data point was actually blue. So this is what the confusion matrix shows. Everything that is a diagonal box means that the model properly predicted the color of the data points. Everything that is non-diagonal means that the model got it wrong. And so this is useful because now we can try to understand what the model goes wrong. So what I can do is to say, I'm going to select all the misclassified data points. So this 2.2% of the data points that were misclassified, I'm going to click it to select it. And there, it means that now if I draw a line here, it's going to select those data points and I can watch what's special about those data points. So if I look into that, so here I can plot like the two data points that were misclassified. And so if we want to understand why they were misclassified, one thing I can do is, which is something that is pretty good about this software, is I can plot at the same time the true data points. So I'm going to create a link here so that I create I will plot the true data points. And now I'm going to also plot the one that were misclassified. So if we look into that, this link here, I want this to be the main data. So I'm going to say that this, I'm taking the real data here, and I want this to be the data that I'm going to plot on this plot. And now I'm going to create a second link here where I want this to be a subset. Here, this confusion matrix is going to capture the data points that are misclassified, and I want this to be a subset. So you have all the data, and within this data, there is a subset of those data that are misclassified. And I want to see which of those data points that are misclassified. So let's see what it looks like now. So what you have here is that you have all the data points with their position X and Y. I'm going to add the color, which is their class. So this is the blue points, this is the red points. And now you have those data points that are highlighted with a field symbol here. Those are the data points that are misclassified by the model. Those are the data points that the model think that they should be red, although despite the fact that they are actually blue. And if you look at those data points, the reason that the model gets confused about this is because they are close to the boundary. So those points that are close to the boundary, it's easy for the model to get confused because it's not really sure if it should be blue or if it should be red. In this case, the reason that the model does not get this right is because this tree model is very simple. One way that you can look into that is very useful is to visualize this tree, to try to understand what it's actually learning. So you can draw a line starting from tree and use this tree viewer thing. And so when you use that, it can actually tell you what was the decision tree. So for example, here in this case, it's telling you that to classify whether a point is red or blue, it first look at the value of y. If y is lower than 52, it will think that it's mostly red. If it's higher than 52, it's going to say that it's mostly blue. And then there is a second branch here, which is that when it's lower than 52, it's going to look further into now the value of x. And if x is lower than 30%, then it's going to think it's blue. And if x is larger than 30%, it's going to think it's red. So this is what the tree is learning on this case. This is the rules that the tree learns. This is how it thinks you can classify those data points into being red or blue. And here, this is a very simple tree with only two levels. Like you have one first branch here and then a second branch here. So this model is not very accurate, and that's why it gets confused here. So one thing we can do is to make this model a little bit more complex. For example, you can say, I want like more, let me see what we can do. We can have maybe a higher tree depth, or maybe one thing we can do is maybe just replace this tree by a forest. So I'm going to do that. I told you that before that a single tree is often not very accurate, and that replacing it by a forest is actually better. A forest is just going to be an ensemble of trees. So I'm going to take a forest model. So I'm going to do the same thing. I take the data, I feed that to the forest. So now the forest is going to be an ensemble of trees. And I can now feed the forest to this widget test and score. And now if we look into this, now the classification becomes 100%. It means that now by replacing the tree by a forest, now the model has a perfect accuracy. It's at 1% of the time it's able to properly classify whether a data point is red or blue. And if you look at the confusion matrix, now every time it's blue, it's predicted to be blue. Every time it's red, it's predicted to be red. And there is never any point here that is misclassified. So this is an example here where a single tree model would not be accurate enough for these data sets. And that you need a more complex model like this forest model here. Okay, so what I'm going to do now within the few minutes that we have left is that, so this is just an example with some fake data points, but now we want to do that with some real glasses. So same thing, I'm going to send you a data set. So here, what I'm going to send you is actually two different data sets. One is a series of glasses for which you know their composition and their classes. So let's see what this data set looks like. Sorry, let me close that. So if you look at this data set, it's going to look like this. So in this data set, you have a series of glasses. You know how much silica, how much B2O3, P2O5, Al2O3, Na2O, CaO. So you have a list of those 6 oxides here, and it's giving you the mole fraction of each of those oxides. But now the difference is that for each of those glass, you know which class it belongs to. So you know if it's a Windows glass, or if it's like a kitchenware glass, like more like a Pyrex glass, like something to use to cook. Or some of them are cover glasses, like more like a Gorilla Glass that you can use to protect smartphone screen. Some are like display glasses, like more like a glass that you can use as substrate on OLED glasses, like more like a Corning jade glass, if you know about this. And some of them are bioactive glasses, like glasses that you can use, for example, to treat bone fracture. So there are some glasses that you can put in the human body, and they're going to dissolve and help bone regeneration. So those are the three families of glasses that you have. And at this case, it's different now because you know this information already. So the goal here will be to train a classification model that can learn from here this collection of 500 glasses, and that can learn to predict based on the composition what type of glass is it. So basically, you will need to do the same thing that I just did, but with this data set to predict which type of glass, what family of glass belongs to based on its composition. So the main difference here, like the workflow will be very similar, but this time you have to when you load your file. So again, you can say either you're going to put the address of the file here, or you will just download this file, put it on your computer, and then open it. And now the difference is that you have more columns, and you have now a feature that you want to predict, something that is going to be your target, your output. So when you load those data, you will need to say SiO2, that's numeric, and that's a feature. That's something you want to use as input. B2O3, that's numeric, that's a feature. P2O5, same thing. Al2O3, Na2O, CaO, those are all numerical feature. But now you have the class. The class is something categorical. It's just something, it's just some discrete choices, can be bioactive, cover glasses, display glasses, kitchenware, etc. And then this is a target. This should be your target. This is what you want to predict. This is, if you want to make sure the model can predict that you will use it as your target, so that the model knows what is an input and what is an output. So this is how you will load the data. And then same thing, that you will connect that to all the things that we did before. Like you can use a tree model, etc. So let's just quickly look at what the data look like. So now it's a much more complex database. Here, if you look at it, it's hard to really understand how you would classify those things. For example, if I look at, I'm going to put SiO2 on the x-axis, and let's say Al2O3 on the y-axis. And each color here shows which class of glass it belongs to. And here, as you can see, because there is a lot of inputs, it's actually very hard as a human to find what is the right pattern here. Of course, you can find certain things, like let's look at, for example, if we look at sodium and calcium, like maybe you can find that the bioactive glasses, they typically contain a lot of sodium and a lot of calcium. While on the other hand, the display glasses, they contain like almost no sodium. So you can come up with those kind of rule as a human, but still, like all of those data, they still to overlap with each other here. So it becomes very hard here to really classify those glasses as a human. But it's going to be something much more simple for a machine learning algorithm. So here, if I'm coming back to what I would like you to do, and I think I can let you think a little bit about this, and then we can discuss more about this tomorrow. So here, what I would like you to do is to take this data set of glasses for which you have different glass composition, and you know the class of each glass. Then you can visualize the data set, like see what you can learn by just plotting the data, plotting the distribution of the variables, etc. Then, just like what we did, you can train a decision tree model that is going to try to classify those glasses into different classes. And then you can check what is the accuracy of this classifying model, just like what we did. by using the test and score widget. Then you can determine the confusion matrix to see what are the classes that are properly classified from the one that are not properly classified. Then, so what you should find here is that if you use a simple tree, the simple tree might not be 1% accurate. So again, you can do the same thing as what I just did, and you can try to train now a random forest model. And you should find that the random forest should have a higher accuracy. And then the last thing that I would like you to do is once you have the model, then you can use it to make some prediction. Remember that's always what we want at the end. Once you have the model, it's one thing to have found a model that can properly classify glasses into different families, but the real value of that is that you want a model that then can take new glasses that it has never seen before. So new glasses for which you know their composition, but you do not know yet what type of family they belong to. And you want to see what the model predicts, what the model think those glasses are. So for this, I'm going to send you a second data set. And this data set is now a list of glass composition for which you just know the composition, but you do not know the actual family they belong to. So let me show you what this data set looks like before we stop for today. So this one is called test. The first one is called training. The second one is called test. This test one, I'm giving you a list of 5 glasses, but for this, I'm only giving you the composition of those glasses, but we do not know the class yet. So the idea would be in this case, once you have trained your classifying model that has learned how to predict for a given glass if this glass is a display glass or a kitchenware or a cover glass or a bioactive glass or a window glass. Now this model should be able for each of those glasses to predict which family they belong to. So those glasses here, those are some glass composition that were not included in the previous data set. So those are some glasses that you do not know yet which class they belongs to, and you want to use your model to guess what class each of those glass belongs to. So that's what I would like to do. So maybe you can think about this, and tomorrow we'll go through that to see how in practice you can train this model and then use it in practice to make some predictions. Okay. So any questions about this? Or any questions about anything we talked about today? Yeah.
How do we add this data file as a test into our models? Do we just add it as a file into the kind of the links we've already got, or do we have it as a new Orange project?
So for this, you will need to use the option which is called prediction. So I think you can look a little bit into that, but like the idea is that once you have your model, so I'm just gonna briefly show you what it should look like. So you will have your model and you have trained the model. So here your random forest model is trained. Then you will link it to this widget, and this widget now becomes able to make some prediction. And so if you want to now use this prediction widget to make some prediction for some new glasses, you will need to load now the new data, right? So those data are the data that are used to train the model. That's the model that are used. Those are the data for which you know already which class they belong to. And here you will now load the data for which you do not know which class they belong to. So you will use like the test data. So that's what I'm going to do here. So in this case, now if I look into that, I look at this table. Those are the data for which you know their composition, but you do not know what class they belong to, right? And then you will take those data and put it to the prediction. And now the prediction, if you look at this, what the prediction will do is to take those data, and it's going to now make a prediction about which class it thinks those data are associated with. So that's the main spirit of how it works. You have this prediction widget. This prediction is going to take some new data as input, and it's going to use the model that you just trained to make some prediction about what it thinks the classes of those glass should be. Does it make sense?
Yeah, perfect. Thank you.
Okay. Any other questions regarding that?
I'm not seeing anything in the random forest widget. It's not showing me any information, or well, actually in the test and score, I guess it's not showing me, so I'm not sure what I'm doing wrong.
So if you want to see, so do you want to see how accurate the model is? Is it what you mean?
I was just setting up the test and score from the random forest, but I'm not seeing anything in the.
So what you can do, right? So is like so you take your random forest and you will attach it to like the test and score, right? So at this point, those two things are connected to each other. If you just do that, then you won't see anything, because the model at the test and score widget at this point only receives the prediction from the model, but doesn't have anything to compare it with. So what you want is to compare what the model predicts with what is the actual class. Okay, so you need to add this line here, and now it's going to be able to calculate the accuracy of the model, because it can compare what the model think is the class of each glass with the actual class that you provided into your data sets. Does it make sense?
Yep, that's what I was missing, that other connection. Thanks.
Sure. Any other questions regarding this? Okay, so I guess if not, we can stop here. So tomorrow, what we will talk about is I will show you an example of an entire pipeline, like starting from the very early steps of how you gather your data, how you clean your data, how you create features, etc., up to how you would select a given algorithm to do your machine learning, and select the optimal complexity of the model. And then in orange, we will see an example of regression. Like so far, we have seen an example of clustering. We have seen now an example of classification. So tomorrow we'll see an example of a regression, where I will I will give you another data set for you to try and to build a regression model within this orange software. Okay, then thank you, everybody. Then